Hi guys, today we're going to learn about linear approximations and differentials. We know that the tangent line to a curve gives you very useful information, especially if you want to approximate a value on the curve. We usually write our tangent line equations in the point-slope form, as we mentioned before over here. Or for a particular value of x1, named a, we could write it as y minus f of a is equal to f prime of a times x minus a. When we're using a tangent line to find an approximation of a value on the curve, we might want to rearrange the terms of the tangent line equation and write this. Technically speaking, what we are moving is this f of a that is negative, positive on the other side. So we have this situation coming directly from the point-slope form. Please note that y represents the y-coordinate of a on the tangent line. This gives you an approximation of f of a. The y-coordinate of a on the function f of x is represented by f of a. F of a is going to be the actual value. So let's start this so you can see that it's not that bad, okay? So this first example that we have over here, we have that f of x is equal to x squared. For a, they are asking, write the equation of the tangent line to f at x equals 1. So as I'm reading the equation of the tangent line, I'm pretty much ready to take the derivative of my original equation. You have that this is going to be 2x, okay, f prime. So for a, what we're going to do here is at x equals 1, we know that my f of 1, aka the point, is going to be 1 squared, which is 1. So I do have, for this one, I have the point 1, 1. In the same fashion, we have f prime of 1. We know that f prime of 1 is going to be 2 times 1, which is 2. And this is technically your slope. So we have all the pieces of the puzzle. So your equation of the tangent line is going to be y minus 1. Okay, minus 1, if I write this correctly, that would be nice. Okay, is equal to 2 times x minus 1. Okay, so that's my equation of the tangent line. Technically speaking, since I'm already knowing where we are going, I would move that 1, that it's negative, positive on the other side, so you have this situation. Okay, so that's the equation of the tangent line. So for B, they are asking you to use the answer to A to find the approximation for f of 1.01. So your approximation, okay, you are going to use the value of 1.01. So it's going to be y, it's going to be roughly 1 plus 2 times, and you have that it's 1.01 minus 1, okay? And then you can do the operations there. What do you have here? What we have is that this is going to be equal to 1 plus 0.02. Okay, meaning this is going to be equal to 1.02, and this is going to be an approximation or estimation. Okay, this is an estimation. Okay, so that's your estimation for f of 1.01. Now for C, they are asking you to find the actual value of f of 1.01. Here we're lucky that we have the original equation, so what we're going to do here is you just plug, instead of x, the 1.01 square, and then you can even type this in the calculator. Okay, so you have that it's 1.0201. This is your actual value. Okay, this is my estimation. Okay, so for part D, they tell you find the amount of error in your approximation. You know that the error, okay, and the absolute value of the error, okay, is going to be what? It's going to be your actual minus the estimation, okay, with an absolute value. Okay, so you have that your actual is 1.0201, okay, minus the estimation, which is 1.02. So you have this, okay. So you do this operation and you can see that the error is going to be 0.0001. Yes. So if it's a good or bad approximation, it will depend on the context of the problem that you have. Okay, but that's the actual error. Okay, so hopefully you got this idea. Otherwise, we're going to do another example over here. So if I ask you here to use a tangent line approximation to approximate the value of cube root of 127, what you're going to do, and technically speaking, you're going to see a question just like that, right? The other part is me trying to guide you what to think. So what you're going to look here is that your function is going to be the cube root of the number. Okay, so therefore you are thinking about this as your function. Then you are going to choose a number that is pretty close to the 127, that it's a perfect square. So immediately as I see the 127, I'm like, I know that my perfect, not square, perfect cubed, okay, is the 125, which we know that it's 5 to the power of 3. Are we okay with that? Also, you are thinking, I'm seeing my f of x over here, so what I want to do for building my tangent line, I need the slope, okay? So I know that the derivative of my f in this equation is going to be 1/3 x to the power of negative 2/3, meaning this is going to be equal to 1 divided by 3, and then you have the cube root of x squared, okay? So that's going to be your derivative. Now, you're going to tell me, so what are we going to do here? Well, you have that your approximation is going to be y equals something, okay? So that something is going to be f of a, okay? So you have that f of a in this equation, this is a, okay? So your f of a is going to be the cube root of 125, okay? Plus, okay, f prime of a, which is going to be the derivative, okay, with the 125 inside, okay? So this is your slope, times the x. What's the x? The x is the 127 minus a, which is 125, okay? So you have all the situations. So this is your approximation, okay? So you keep going here. So you have that you actually, this should be squigglies here, okay? So because it's an approximation, so you have that this is going to be equal to 5, okay, plus 1 over 75, and this is going to be a 2. So this is equal to 5 plus 2 over 75. You can leave it like this, or you can actually do the operation. I believe that is 377 divided by 75, and that's going to be your approximation, okay? So you can say that this approximation, okay, is roughly 377 divided by 75, okay? And that's going to be your approximation. So back in the day, Leibniz used the notation dy dx, the one that we used, to represent the derivative of y with respect to x. The notation looks like a quotient of real numbers, but it is really a limit of quotients in which both the numerator and the denominator go to 0 without actually equalizing to 0. So Leibniz did most of his calculus using dy and dx as separate entities, but he never quite settled the issue of what were they. To him, they were infinitesimals, non-zero numbers, but infinitesimally small. It is very tricky to define dy and dx as separate entities, but since we really only need to define dy and dx as formal variables, in general the calculus textbooks define them in terms of each other so that their quotient must be the derivative. Okay? So what is the formal definition of a differential? We say that y equals f of x is a differentiable function, then the differential dx is an independent variable. The differential dy is equal to dy equals f prime of x dx. The variable dy is always a dependent variable, and this one depends on two things, x and dx. So if I ask you, hey, find the differential dy given y equals 5x cubed, what you're going to do is go back to what we were doing when we were doing derivatives. So if I ask you to take the derivative of that, you would tell me immediately dy dx is equal to 15x squared. Are we okay with that? So what you're doing here is you are using the resources that I gave you before via the power rule. But this is not the differential. The differential is going to be dy equals 15x squared dx, and this is your differential. This is the differential dy, and that's it. Wasn't that easy? So now let's apply it a little bit here, okay, so you can see how fun it could be. Okay, so we have over here, okay, we have the radius of a circle that increases from 10 to 10.1 meters. What we want to use is the differential dA to estimate the increase in the circle's area A. Okay, so we have that the circle's area is A. So you have that A is going to be equal to pi r squared. Okay, at the same time that you're reading the question, okay, so they are telling me that they want me to estimate the increase. If it's increasing, I'm going to measure this as my original, then this as my endpoint. So di is going to be positive 0.1, okay, because it's increasing, okay. After that, you're like, okay, let's take the derivative of the area with respect to r. So you have that dA dr is going to be equal to 2 pi r, okay, so that's what we have. Do you agree with that? In the same way that you have that dA, the differential, is going to be equal to 2 pi r dr. Now, ask yourself, do we have all the pieces of the puzzle? And the answer is yes, we do. Okay? So, our approximation here is going to be 2 pi times r, which is 10, times dr, which is 0.1. So, this is really nice. Why? Because you have that this is 2 pi. Okay? This is your estimation. Okay? So, dA is roughly 2 pi. This is an estimation again. Okay? Now, compare the estimate we found in A with the true change delta A and find the error in your approximation. Okay, so what we know, since we have the equation of the area, okay, you know that your initial area, or area 1, is going to be pi 10 squared, which is 100 pi. Your second area with the 10.1, you know that the area, I'm going to call it area 2, is going to be pi times 10.1 squared, and that value is going to be 102.01 pi. Okay, this is my actual beginning and the end. So I do know that my delta A, okay, the true change, okay, is going to be this minus this, right? So you know that it's the 102.01 pi minus the 100 pi. Therefore, my delta A is going to be 2.01 pi. So, now, what is the actual error? Okay, so I found my delta A, find the error. My error is going to be, as usual, okay, the actual minus the estimation. So you do know that it's going to be 2.01 pi minus 2 pi, which is going to be equal to 0.01 pi. Okay, and that is your that's going to be your estimation. Okay, your error, excuse me. Okay, and that's pretty much it. I hope that you find this video helpful. Bye.